Hello, my calculus doing friends. We're going to be looking at 12.5 in this video, which is equations of lines and planes. And so let's get to it. We'll do it right now. Here we go. Here we go. So let's see. I go on paper view. Oh, did I record? Yeah, I recorded. I go on paper view. I go on light. I go on dropping my calculator on the floor. And I didn't get a pencil. Nope, here's my pencil. Okay, I have everything. Okay, so the equation in R2, to define a line, we just needed two things. Do you guys remember what those two things were? We needed the slope, and we needed a point and or the y-intercept. And it was better if we had the y-intercept. If we had just any old point, then to come up with the equation of the line, we could use point slope, which was y minus y1 equals m times x minus x1. It's just a formula where your point was x1, y1, and you just crank that handle, that's a comma there. And you put your slope in there, your slope was m, and you just crank that handle out. You could solve that for y equals mx plus b, where b stands for the y-intercept, and that could be put in standard form. And so all of those things we did in our algebra class. And so it kind of makes sense, seems like it would make sense, that all you'd have to do is add one more term when you went to R3, when you went to 3 dimensions, a CZ, and then you would have it. But I hope that you remember that we did look at, is this, should I be zooming in just a little bit on that? This is a new thing. No. Right there. And then maybe it's a little bit clearer. Are you going to focus? Yes. So in R3, though, we saw that, and in fact, we graphed a bunch of them. The ones we graphed all had x and y be 0, and then we graph that, or x and z be 0, then we graph that, and then we had one where we let one of them be 0 and the other two be non-zero, and we graphed that, and you guys had beautiful drawings, and my drawings were not that beautiful, but anyway, that's what we said. But you guys remember, that wasn't a line, even though it seems like it would extend right over. This was a plane. And so we're going to be wanting to come up with the equation of a line. And so we're going to be talking about, well, what things do we need to come up with the equation of the line? And it's actually kind of genius the way that it's going to be done. So to describe a line or a curve, we're going to start off with a line, and then we're going to do curves in chapter 13. But lines in chapter 12 here. In 3D, you must parameterize, that's hard for me to say, the line or curve. Equivalently, you can use a vector valued function, and the basic idea is to describe the curve by describing a vector that points to the curve. And so we're looking at these vectors that point to the curve, and we're looking at the terminal point there as a point on our curve, and it points there, and that's a point on our curve or on our line. And here's another vector. And it points to our line or our curve. And so we're just using the head of our vector as a set of ordered triplets, right? To be a point on the curve. So in R3, I'm moving my T out of the way, although I don't want it to get too far. And so in order to define a line in R3, we're going to need two things, just like we needed in R2, but they're not going to be slope and a point. It's going to be something that's kind of similar to slope, and that is something called direction. And so direction, and we also need a point. And you're going to see that this direction is going to be a vector, and so that's what we're going to be doing. Then from these two things, from the direction vector and a point, we can create the equation of a line in 3 different formats: as a parametric equation, as a parametric equations, as a symmetric equation, as a vector equation. And next we will build the first two forms, and then the book does the other forms. So, and actually you can get to, from what we're going to build, you can get to their form as well. They do it a little bit differently, and I think that you'll enjoy this. You'll love it. It's great this way. Sorry. So here we're going to be building the equation of a line in the parametric equations and the symmetric equation form. And we're going to start off with a point on the line. I'm going to call it p sub 0, and it has the coordinates x0, y0, z0. And then we're going to be given the direction. So those are the two things that we said that we needed: the point on the line and the direction. And here's the direction vector where it has the pieces A, B, C. And A, B, C are called the direction numbers. And I'm going to draw you a quick little visual of that. It's going to be beautiful, and so everyone will love it right here. So this is my z-axis kind of going here, and my x-axis, and my there's my x-axis and my y-axis. And I'm going to pretend that my point is some point right here. So there's my p naught. I might want to put that just a little higher, just so that it's out of the way. So there it is, my p naught. And I'm going to put my direction vector on here. So I'm going to say that this is the point ABC, right, would be the point ABC. And then my direction vector would be right there. And I'm going to call that direction vector right there. And so there it is. Now, how you start off here, that means that my, I had an eraser, a better eraser, but I have what I have. Okay, so we're looking for a line that goes through this point in this direction. So they should be parallel to one another. So there I have drawn the line that we are looking for. Now there are infinitely many points on that line, and I'm just going to pick one of them. And I'm going to just put that point right here that I've just picked. I could have picked any point. I could have picked a point over here or wherever have you. This is just arbitrary. I'm going to call that point P, and I'm going to name the coordinates of that point X, Y, and Z. And so there is a vector that goes from P0 to P, and I want to talk about that vector. So there is a vector that goes from P0 to P. And I'm going to draw that vector right here a little bit darker here. I should have color pens since I could have, but I don't have it. So there's that vector right there. Now, what I know about that vector is that vector P naught P is that it is parallel to the vector V. And that means that they are scalar multiples of one another. And so that scalar value, I could pick any value for that. So I'm going to pick T for that. And remember, when you did parametric equations in pre-calc and in Calc 2, that's the typical variable that they used for that. And so we know that that would be T multiplied by our direction vector V would be equal, because they're parallel, where T can be some real number to make that true. And so how this is going to go then is now I'm going to find the position vector here. And so this is going to be here x minus x naught, right? Because you start with P, x minus x naught. And so I'm going to have a vector here, x minus x naught, and then y minus y naught. So y minus y naught, and z minus z naught. And that's going to be equal to, and I'm going to go ahead, remember this is ABC, remember our ABC, and I'm going to go ahead and distribute the T in there just to save myself a step. So this is TA, TB, and TC. And then with vectors you can equate the components. So that's the next thing that I'm going to do, is I'm going to equate the components. So this would be x minus x naught equals TA, and then y minus y naught equals TB, and z minus z naught, equating the last pieces, is TC. And then my plan is to solve for x, solve for y, and solve for z. So I get x equals x naught, if I add x naught to both sides, plus TA. And you could also put AT, it doesn't matter at all. And so, and y equals y naught plus TB or BT, whichever makes you happy, and z equals z naught plus TC. So we did a lovely job on that, and actually these are the parametric equations of our line. And notice the two things that you have kind of going in here is you have the point x naught, y naught, and z naught, and you have your direction numbers a, b, and c, and then you have some parameter t. And so, and I'm going to say that t is an element of the real numbers, and so I have t as an element of the real numbers. And then so this is called the parametric equations. I'll write that right here. The parametric equations. If I take each one of these and I solve it for t, so that's what I'm going to do next, is I'm going to solve for t. So solving for t. So if I solve for t, I'm going to take away x naught, right? I guess go back to here, right? And then divide by a. Is that okay? So x minus x naught divided by a equals t. And same here. I'm just going to go back a step here, and all I have to do is divide by b. So y minus y naught divided by b. And last but not least here, z minus z naught divided by c. Oh, I was going to say that equals t. Equals t. I'm going to move that one over. You're going to be like, why be so picky about where you have it on the page? And I'm going to be like, yeah, I know. I agree. Okay, this was b though. Equals t. And since they're all equal to t, and every single one of those is equal to t, you can set them equal to each other, and this is called the symmetric equations. So a x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So see how it wasn't very hard to come up with, and these are called the symmetric equations. Okay, and then I just summarized that here in this box. And but there's something I should have had in this box as well that I didn't have, and I'm going to put it in there as well. So if you're trying to find the equation of a line in R3, and you're given the point, and you're given a direction vector, then the parametric equations look like this. And if it's better for you to write AT instead of TA, you can. It doesn't matter. I think the book did AT, and then when I typed it, I got TA. It does not matter at all. And so where t is any real number, the symmetric equations are here, just like we just built. And then the vector equations, and this is where I wish I would have put some stuff, so I'm going to put that down here. I have my yoga blocks holding up my monitor, and so I have to move my paper around those. But this is going to be the vector equation, and they call the vector equation R, so we're going to be calling that R, which is R naught plus t times our direction vector. And they tell us that R naught is that vector that it was the terminal point of a vector that goes to our point on our line. And so this is then telling us that x naught, y naught, z naught, so this is a vector there, plus, and then t times ABC, remember that's what V was, and so this is TA, TB, TC, and then you can put this together, and this would be x naught plus TA, that's my vector, and then y naught plus TB, and z naught plus TC. So this is R, my vector R. And then if you wanted to write that in IJK form, you can. This is x naught plus TA. This is what they typically do in your book. And then I. And are you still able to see that? I'm just going to scoot that over. I'm trying to go even here. Y plus TB, J, and then plus Y naught, right, though, right? And a Z naught plus TC, K. And my little hat's on there. Okay, so I did a lovely job on that. So that's what we're going to do next is some examples. Oh, I wish I would have grabbed a ruler, but I didn't. This way. I'm sorry, I'm figuring it out still. I think I'll get better at it. I might not get better at it. Maybe I will get better at it. Wish I would have grabbed a ruler. Okay, I was careful not to forget my T though. Okay, find the equation of a line through the point 1, 0, negative 3 in the direction of 2, negative 4, 5. And so if I'm coming up with those parametric equations, remember it's just very much a formula. X equals X naught plus TA, right? And so in our case, X equals, and then this would be 1, because this is our X naught right here, our Y naught and our Z naught, and then our A and our B and our C. So plus 2T, so plus 2T, and then Y equals Y naught, which is 0, and then minus 4T, so minus 4T, and then Z equals, so this is etc., right? I didn't write them all, but just to get the plan on it, right? And which is Z naught, so instead of having x's, we have Z, so Z naught, which is negative 3 plus 5T. So we did a lovely job on that, and then you can solve those for T if you like, or you can remember the form that they go in. Is X minus X naught over A, and you can just put them in if you like, and then the same for the Y's and the same for the Z's. So your choice on how you do that. If you do this, and this would be X minus 1 over 2, and that would equal Y minus 0, so just Y, over negative 4, and that would equal Z, and then it's minus negative 3. Minus negative 3 is positive 3 over 5. And so we did a lovely job on that. And then to write it in vector form as a vector equation, I like to just use this right here. And then you can, the book does their answer a lot of times in I, J, and K, although you can do it with the vector brackets instead of I, J, and K. Your choice on that. And so, so my vector R is going to equal 1 plus 2T I plus, and then negative 4T J. Yeah, and you could have had that as minus. That would have worked out okay as well. And then plus negative 3 plus 5T and K. And I know I need a little bit more room on here, maybe next semester for the real students. I'll put a little bit more room there. And then if I pick some points, like for example, if I pick T as 0 and I put it into, this would be the equation that I would want to go and use. If I put in 0, then I would get the ordered triplet 1, if I put in 0, 0, and if I put in 0, negative 3. And I hope that you're saying, oh yeah, well, that's just that point right there. And if I put in 1, then I would get the ordered triplet. If you put in 1 here and you do that arithmetic, 1 plus 2 is 3. And if you put in T as 1, and I'm putting it right in there, I get negative 4. And if I put in 1 right there, you get negative 3 plus 5. That's 2, right? So I get 2. And this is where I kind of wish I would have brought a ruler. And so, I wonder if there's something that would make a straight line in this drawer. There is, and I'm going to use it. Okay, so if I plot these points, so from the center, from the origin, I'm going to go in the positive x direction 1. I'm going to go in the positive y direction 0, so don't move. And then I'm going to go down, z is up and down, so 1, 2, 3. And we've talked about the fact that we're drawing something that is three-dimensional on something that's two-dimensional, and so it doesn't look perfect, but it looks as best we can do. 1, 2, 3, and then in the y direction -4, 1, 2, 3, 4, and in the z direction 2, 1, 2. And then I grabbed this book out of the drawer there. It's about fun places to go on Highway 395. I'm going to draw that line in there using my book. And I just want to get another point just so that you could see that the other point would fall on that line. Like if I get 2, and 2 times 2 is 4 plus 1 is 5. So this point would be 5. And -8. And putting in 2 here gives 10, minus 3 is 7. And so that's probably going to walk right off my graph, but I'm going to just do my best to plot it. So 1, 2, 3, 4, 5 over 8. 1, 2, 3, 4, 5, 6, 7, 8, right? And then I have to go up 7, and so I'm just going to use that distance here. So if I go here, 1, 2, 3, 4, 5, 6, 7, that's that distance right there, and I'm just going to put it on there, right there, and there's another point on that line, and I expected it to be. Okay, we did a lovely job on that. You can put arrows on here. Later on, we're going to be looking at the direction things are going, and they'll put the arrow in the center when they do that, when they look at the direction. Okay. This example here, the next example, so I'm going to go over, I hope I wasn't off the screen the whole time. This next example here is, what if your direction number is 0? And so I was looking to see if it had the time that I've been recording, but it doesn't. I wish it did. I think it did last semester when we did set this up, but this is on my different, I have a new computer because my other computer stopped working. What is the direction, what if one of the direction numbers is 0? And what if you get fractions in your direction vector? Then, here's some things that you can do. And so find the equation of the line through these 2 points. So what you need is you need a point and you need a direction vector. They gave me 2 points and not a direction vector, but good news is that you can use, I can call this P and this point Q, and then you can find PQ, and PQ can help you find your direction vector. And so I'm just going to do the component form, how you subtract here, so it's going to be 1, take away 1, which is 0, and 3 halves, take away -2, which is plus, right? So 3 halves plus 2 is 1.5 plus 2 is 3.5. So I'm going to get a calculator. You guys are like, are you kidding me? You're going to get a calculator for that? And I'm like, yeah, I've had a pretty rough day. So I could find myself making a boo-boo. So here's my calculator, and I just put that in my calculator. 3 halves minus -2 is 7 halves. Then the last one I want to do is 3. Oh, did I divide? Oh yeah, I did, because I didn't do my fraction. So 3, and then take away negative, I'll do a fraction this time. Take away -3 halves. So 3 plus that, so 9 halves. Now I could use this as my direction vector, or I can use any scalar multiple of this as my direction vector. So like if I wanted to, I noticed that, well, these are both divided by 2 and have fractions. I could take this and I could multiply by 2 and then call that my direction vector. So I could multiply by PQ by 2 and then call that my direction vector, which if I did that would be 0, 7, and 9. And so if I like, I can definitely do that. And so the parametric equation here, I can use either P or I can use Q. And remember when you do your parametric equation, right? X equals X naught plus TA, right? So I'm going to be putting that in here. This is my A, and this is my B, and this is my C, and this is my X naught, my Y naught, and my Z naught for my point. And so this is X equals, and then 1, and then 0t plus 0t, which is just makes the t go away. So I'm going to put x equals 1, and then we're going to have comma y equals, and then negative 2 plus 7t, and then z equals, and then negative 3 halves plus 9t. And so we did a lovely job on that. And when you go to put this in the symmetric equation form, there's no t to solve for here, so it's just x equals 1, and then comma, and then you could solve this for t. If you do, you would get y plus 2 over 7, or you could put it in the form by saying to yourself, instead of x, y, x minus x, y minus y naught over b, right? You could do that too. Either way, it's good. It's all good. However you do it, that's fine. And then solving this one for t as well is going to give me z plus 3 halves. And I'm just going to leave that complex fraction in there divided by 9, and that's okay. And then my vector equation, so I'm going to get my vector equation, and I'm going to put it here. Since I did this one in IJ and K, which the book normally does, I'm going to do this one in vector form, or with the bracket, the angle bracket for the vector. That's what I'm thinking I will do here. So this for x is 1, and for y is negative 2 plus 7t, and for z is negative 3 halves plus 9t, and where t is any real number. And then I want to sketch this, and you know, oh darn, there went some yoga blocks that were holding my paper down. Oh well, it's okay, it's okay. Life goes on here. And so there's no worries. So t is 0. If we let t be 0, then that gives us the point 1 and negative 2 and 3 halves. And so, and that's a point we already knew. And in fact, we were given that point from the beginning. And if I let 1 be t, I get, when I put it in, I get x is 1. And when I put in 1 here, I get 5. And when I put it in here, when I put in 1 here, that'd be 9, take away 1.5, which is like 7.5. And of course I have that point Q too, and so that I could use. And so down 1 over y negative 2, and then down 1.5. I just kind of estimated that the best of my ability, so I have that point there. And then over 1, and then down 5 on the z direction, the y direction. 1, 2, 3, 4, 5, then up 7.5. 1, 2, 3, 4, 5, 6, 7.5. And then I'm just going to try to plot that point on the line and just see how we do with that point on the line as well. And so down 1, over 1.5. And then this is where it's kind of tricky, because you have to go up 3, and you can't use what you got on here. So you really do almost, I wish I had my 3x5 card, but I don't. So I'm going to mark it on here. 1, 2, I'm going to mark it on here. 1, 2, 3. And so 3 is this distance. So I went over 1. Did I get a mark on there? 3 is this distance. 1, 2, 3. Yeah. Okay, so over 1 on the x direction, 5 in the y direction, 2, 3, 4, 5, and then I want to go up. What did I do wrong? Because that's not hitting on there at all. Oh, I did 5 in the z direction, and I wanted to do 3.5 in the z direction. Sorry, I'm trying to plot Q. Pay attention to myself here. Down 1, over 1.5, and it wasn't going on the line. And when it wasn't kind of falling on that line, so this point is about here, I was like, what the heck? Something is going on. And what was going on is that I was picking up the 5 from here instead of the 3/2 from here. And so, and then when I draw this line in here with my straight edge of my book. Now, one thing that I didn't show you, but I do want to, I meant to show you, and so I'm just going to back right up to this problem right here. I just wanted to put the direction vector on here. Here's our line. And I just want to put the direction vector on here, which was 2, -4, 5. So if I go down to 1, 2, and I go backwards -4, 1, 2, 3, 4, and then up 5, 1, 2, 3, 4, 5. And then I'm going to use my book. Remember, the direction vector goes from the origin to, that's the terminal point on the direction vector, the head of the vector. Okay, so there's that direction vector, and you notice that direction, I wish I had a colored pen to make it stand up a little bit, but the direction vector is parallel to, and that's what we expected, and so parallel to our line, because that's what it was telling us was the direction it would be in. You could do that here too, for this one down here. And you could either use this as your direction vector, or you could use this as your direction vector. It would work. And so anyway, either one would be good. Okay, so we did a nice job on that. And our next story is asking us about lines that are skew. And this is drawn in a cube, so that you're looking at the bottom. So it's a line on the bottom of the cube, and then another line on the top of the cube. And those lines are never going to intersect one another, but they're not parallel. And then here they just kind of have two planes, and you can see that the planes are parallel, but you have lines that are not parallel in those planes, and they're skew. And then this one was trying to draw it in 3-dimension. Anyway, if you ask Megan about this, Megan's going to be getting some rulers out and showing you some. So so here's the idea. They've given us line 1 and they've given us line 2, and if these two lines, they're asking us, are they parallel, or are they skew, or are they intersecting? And if they're parallel with one another, then that would mean that their direction vectors would be parallel with one another. And I hope that you're remembering, I hope that you're thinking about when things are parallel, that they are scalar multiples of one another. So so if I want to come up with a direction vector, remember we call the direction vector V. And so if I'm wanting to come up with a direction vector here for line 1, so that's going to be V1. Make a little vector thing. And remember that the A, the B, and the C are, this is in symmetric equation form, right? And the A, the B, and the C for our direction vector are located just right there in our denominator. If you're kind of remembering, it's x minus x naught over A, and equals y minus y naught over B. And so right here is just giving our direction vector right there. And so that's 4, 7, negative 5. And then for, I hope that you're ahead of me, for the direction vector for line 2 is 8, 14, negative 10. And the first thing we ask ourselves are these scalar multiples of each other? Because if they're scalar multiples of each other, then that means the lines are parallel. And yeah, they are, definitely. If you take V2 and you multiply V1, the vector V1 by 2, you will get V2, right? Because 2 times 4 is 8, and 2 times 7 is 14, and 2 times negative 5 is negative 10. It has to work for every single component. And so because of this, because this is true, because they're scalar multiples of one another, we know that line 1 is parallel to line 2. And then we'll do another example here. And this is in parametric form, right? Line 1 is in parametric form. Line 2 is in parametric form as well. They've used S's so that we don't confuse the T's and the S's with one another. Sometimes some books will use T1 and T2, so that these are all T1s and these are all T2s, but they're just saying that the parametric, that variable, that independent variable that you have, doesn't have to be the same, and so they're just using a different variable, so that you know that, hey, they're at the same time, they're not the same. So the first thing I want to do is I want to identify my direction vectors, just like I did on the last one. Now, kind of remember, when they're in this form, it's x equals x naught plus at, and so it's the coefficient, the direction vector is the coefficient of t. So my vector, I'm going to call that 1, vector 1 there, and so just using the coefficient of t, this is negative 2, negative 3, and 1. That's my direction vector. And then for my line 2, my direction vector is, it's going to be the coefficient of s in this case, which is that we parameterized it with s. So this is 1 and 2 and negative 1. And so you can see that, well, they're not scalar multiples of one another, because if I multiplied 1 times negative 2, I would get this. But if I multiplied 2 by negative 2, I don't get negative 3. And so all it has to do is fill on one of them and one of the components. So they're not scalar multiples. So that tells me they're not parallel. So then I want to find out if they intersect one another. And how I would find out if they intersect one another is that I'm going to have to use two equations to unknowns to do this. So I want to make it as easy as, and then I'm going to have to check whether or not it worked. And so it's kind of a sneaky way of doing it. But I want to check, are any of these opposites of one another? And you can see that none of the coefficients for t are opposites of one another. If they are, then you want to choose those two components, and so you can see that the x component and the z component have the s's opposite one another. So that's why it's going to make it just a little bit easier, not a lot easier, just a tiny bit easier. Just saves me one step if I notice that. If you just used always x and y and then made it so that you could solve it for s and for t, that works too. But I always look to see if I can get a freebie, and then in this case the freebie is going to come by using x and z. So when I equate x and z, so that's what I'm going to do. So 1 minus 2t equals, equating it with the x, minus 3 plus s. And then I'm going to do that with the z. Minus 2 plus t equals, and then the z over there is 3 minus s. And because these knock each other out, I'm not going to have to multiply so that you knock out the s or knock out the t. It's already done. It's already, all I have to do is add the equations together and they're going to knock each other out. So when I add the equations together here, I get -1. And here I get negative t. And here I happen to get 0. And whatever I get is what I get. But I want to eliminate either s or t. And so the s's eliminated themselves for free, and that was hot diggity dog. And so now we're on solving for t. So -1 equals t, and then we're going to use what we just found about t to find x. And I can use any s. We can use equation x or we can use equation z. It doesn't matter. I'm going to use equation x just because it's first and the s is positive. And so, but my choice doesn't matter. Life will go on no matter what I do here. And so let's see here. I get 3 equals -3 plus s. So that tells us that s is 6. And so now the next thing I want to tell myself is if they intersect, then t would be -1 and s would be 6. But I don't know for sure that they intersect. And so I'm going to see if they intersect because they would be at the same point when t is -1 and s is 6. So if they intersect, I'm going to, people in class have already told me, make your boxes bigger. So I'm going to draw a line so I can use this space here to put my stuff in here. But if they intersect, it would be when t is equal to -1. Now, when t is equal to -1, we get a point. So I'm going to put in here -1. So this is a point on line 1, and it should be the point of intersection if they're intersecting one another. So when I put in -1, I get 1 plus 2, right, is 3. So this point would be 3. And when I put in -1, and I do the arithmetic there, that's going to become plus. So this is going to be 2. And when I put in -1, so I'm putting that in here to line 1, -1, I get -3. And then I'm going to use s equals 6, and I'm going to come up with a point on line 2 where I'm thinking they might be intersecting. And in fact, I know because I made x and z work that x and z will be the same, and all I'm really checking is whether or not their y coordinate is the same. So, but I like to plug it in just to make sure. So when I put in s is 6, I get -3 plus 6 is 3. And you notice that's the same, and I knew that I made them the same over here. And so I knew that was going to happen. And then when I put in 6 here, I get 12 minus 2 is 10. And I was wondering if that was going to be the same. And when I put in 6 here, I get 3 take away 6, which is -3. And you notice that those are the same. And so really, I'm looking at whether or not these are the same. If these are the same, then they intersect, and that's the point that they intersect at. And that was what we were asked to find, is whether or not they were intersecting, and if they intersect, at what point. And so, but that point is different, and so they do not intersect. So they do not intersect, and they're not parallel, and so there's a fancy name, intersect. Have I spelled intersect wrong? I think I have. I think I've missed some letters here. Just one letter, maybe. Do not intersect, right? And they weren't parallel, so that means there are skew. So we did a lovely job at that. It was beautiful. And so we're going to try the next example. So here we go, friends and family. And so determine whether the lines L1 and L2 are parallel with one another, or if they're skew, or if they're intersecting. If you're a guessing person, we've seen one that's parallel, we've seen one that's skew. You're probably going to guess that these are intersecting with one another, and I've given it to you in the vector format. not with i's and j's and k's, but in the other vector format. So there's two vector formats, and so anyway, and so in this spot, remember this is x naught plus ta, and where a is your direction vector, because you need your direction vector in order to look at whether or not they're parallel. So v1 here equals -1, -2, and 1, the coefficient of t. And then v2 equals, and so for the direction vector, it's the coefficient of s, 3, 2, 1. And you can see that, oh, they're not scalar multiples of either of one another. So not scalar multiples. So that means not parallel. So then the next thing I can see that through there, and I can take that off, and that makes it just a tiny bit better. And so the next thing is to see if they're intersecting. And if you have, and coincidentally, I tried to change this example so that it was X and Y that was good, but I don't know, when I changed it, I think I forgot to edit it. But anyway, it's X and Z that's good, because it'll cancel out the T's on a natural. You don't have to do that, but if you do, then it just is kind of nice. Nothing will cancel out on the S's, right, on a natural. So I'm going to be using to see if they intersect, if they cross. And so I'm asking myself, intersect? Question mark. I don't know if they will or not. And then I'm going to equate the X's and the Z's. I said would be a little bit easier. And so then I wrote Y. And so this is to be 1 minus t equals 2 plus 3s, and t equals 1 plus s. So when I add the equations together, the t's drop out automatically, giving me 1 over here and give me 3 plus 4s. And so when I take away 3 from both sides, I get -2 equals 4s. And so I'm going to be getting that s equals -1/2, right, when I divide by 4. And so -1/2 equals s. And then I'm going to plug in that s is -1/2, and I can use either one of the equations. I can use x or I can use z. And z is just a tiny bit easier to use to find out what, so z, and when I use the z equation, I don't mean z equals, but dot dot, when I use the z component, I get that t equals 1 plus -1/2, or that t equals 1/2. And then I'm going to do that same thing. I'm going to draw my line and complain about the fact that there wasn't enough room here. And so that's the plan anyway, right? And I'm going to say that if they intersect, it will be at when t equals 1/2, and we're going to find the point on line 1, right? So we're going to put in 1/2 here, and I know that it's a vector, but we're looking at it as the point is because it's pointing to our line, that vector pointing to. We're looking at the ordered pair at the where the at the arrow at the head of your head of your vector there. And so we're going to have here 1 minus 1/2, and 3 minus, and then 1/2. So it's 3 minus 1, and then 1/2, right? And so let's see here. This is 1/2, 2, and 1/2. And then s is -1/2. And remember, and this is going to be the point on line 2, and we're asking ourselves, is this where it intersects? And we know already that x and z should be working. So if x and z are not working, that means we have a mistake, and that gives us an opportunity. That's the only reason I check them and find them. And so this is 2 plus, and then 3 times negative half. And so I'm going to put that in my calculator. 2 plus 3, and then times negative half. So I put that in my calculator and I get half. And I'm like, okay, I knew that was supposed to work, right? And then I'm going to put in negative half into the middle. So 3, I don't give myself enough room here to write it. 3 plus 2 times negative half. That's negative 1. And so this is 2. And then I'm going to put it in the last one, 1 plus negative half, which is half. And you can see that they're the same. And the only one that I was concerned about was if the y's were the same, because I had made x and z be the same. And so this means that they are intersecting. And they intersect at the point half to half. So that's where they're intersecting. Then the next thing they asked us is they said that, hey, if they're intersecting, they wanted us to find the angle between line 1 and line 2. And so in order to do that, the thing that you would notice is that that would be the same as the angle between their direction vectors. And we want to find the acute angle. So they intersect one another somewhere. The two lines intersect one another somewhere. And the two direction vectors also intersect one another somewhere and at the same angle. And when they intersect, when two lines intersect one another, they either intersect at a right angle, and then all of the angles would be 90 degrees, or if they intersect a little bit off of a right angle, then you'll have an acute angle and an obtuse angle that they intersect at. Here they're asking us for the acute angle that they intersect at. And I don't know if you guys are remembering how you can find an angle, but you can find an angle of intersection between two vectors if using the cosine. And so this is just a formula. So I'm going to write this formula down. Cosine of theta equals vector 1 dotted with vector 2 divided by the magnitude of vector 1 multiplied by the magnitude of vector 2. And so, and then find theta, and that will give you the angle. And that angle will either be an obtuse angle or an acute angle. I can show you how to guarantee that it is an acute angle here. And so I'm going to dot these together. Here's my vectors up here. And when I dot them together, I'm getting, remember when you dot them, you multiply them together and add. So this is going to be negative 1 times 3 is negative 3. And I add that with negative 4. And I add that with 1. Is that okay? So negative 3 plus negative 4 plus 1. And then divided by, and then we want to square, right? Square, add, and multiply. So, and then take the square root. Square, add, and then take the square root, not multiply. And so when I square negative 1, I get 1. When I square negative 2, I get 4. And when I square 1, I get 1. And so I want to find the magnitude. You square them, add them, and then take the square root of them. And we're going to do the same for V2. So we're going to square this, that's 9. We're going to square that, that's 4. And we're going to square that, and that's 1. And so we get this for our cosine of theta. And so when the dust clears here, we get the cosine of theta equals, in the numerator there, I got negative 6. And in the denominator here, I got the square root of 6 and the square root of 14. If I want this to be the acute angle, and right now, because this is negative, it's going to be the obtuse angle. And the reason is that if you just look at where your cosine is, if you have, when your cosine is negative, it would be from the origin to the second quadrant past 90. And so, because that's where the cosine, I didn't put it up here. I meant to. All students take calculus, right? And so if you're negative, if your cosine is negative, and cosine, arc cosine only goes around in quadrant 1 and quadrant 2. I don't know if you guys remember that. And if you're negative, then that means it's the obtuse angle. So if you want the acute angle, you just do the positive. So since I want acute, I asked for acute, the small angle, then I'm just going to look at this as the cosine of theta equals 6 over the square root of 6, square root of 14. I believe your book says do the absolute value if you want the acute angle, and if you do the absolute value, you certainly will get the positive back. So, and then that's going to make my angle, my cosine, be positive and come in the first quadrant when I arc it, right, when I do the arc cosine of it. So I'm going to get theta equals the arc cosine of 6 over the square root of 6 and the square root of 14. And I'm going to go ahead and put that in my calculator and get a nice value, because I want the exact value. Well, it says to find the round to the 10th, so I guess it didn't ask for the exact value, but I'll give you the exact value here. And I just kind of want to, and so if you don't have a calculator that makes things nicer, like rationalizes the denominator and that kind of thing, then I kind of would recommend that you get one. I think it's kind of nice to everyone kind of have a form that they put it in. Makes it easier when you're comparing with each other and whatnot. So this is the square root of 21 over 7. And then I got to make sure that my calculator, I'm going to do the, I'm going to round to the 10th. And so I got to make sure that my calculator is in degrees. To find that angle, it didn't say in degrees here, but that's usually what they're wanting. And so I'm going to remind myself to make a note of that. So my calculator, that's not how you do make it into degrees. So unit angle, I want degrees, and then I'm going to do the arc cosine of the square root of 21 over 7. And so I'm getting 49.1, it said, to the nearest 10th degrees. So we did a lovely job on that. It's beautiful. Okay, so on to the next one. You're like, hot diggity dog. And so now we're on finding the equation of a plane. And I'm looking for my papers that I put out here on the desk. Sorry to have blank screen there. And so that's kind of the next story, is equations of a plane in R3. And I thought it was funny to put an Air Force, I think that's a KC-46, and I think it's fueling at maybe at F-15. I'm not exactly sure on that, but it is fueling, so I thought it was really funny to put that on there. But this is the kind of plane that we're really talking about. In R3, to define a plane, we will need a vector normal to the plane and a point on the plane. And the reason that we need a vector that's normal to a plane and not just a vector in the plane is that there are lots of vectors in the plane. And here's another one. I'm going to draw another one over here. Here's another vector that's in the plane. And so there's that vector in the plane. And those vectors in the plane don't necessarily have something in common. But what does have in common is that every vector that is normal to the plane, every vector that is normal to a vector that is normal to the plane is normal. Every vector that is normal to the plane is parallel to each other. And so if it's normal to the plane, then they're parallel to one another. So all of these normals will be just scalar multiples of one another. So that's kind of the idea. And I wanted to build out the equation of a plane, and then I've summarized it down there below just so that you could see kind of how it goes. So again, the point P naught is x 0, x, y0, z0. We're going to call the normal vector ABC. That's what we're going to use for our direction, is the normal vector. And it has to be orthogonal to the plane. And so they don't call it V, they call it N for normal. And then we're going to have this point here, X, Y, Z, that point P. And so we're going to start off just the same way we did before. P naught, P, that vector right there. And we know that that vector is equal to, so when you take away, right, x minus x naught, y minus y naught, and z minus z naught. And so now we're describing this vector that goes from here to here. And so that's that vector right there that goes from P naught to P. And since we've got this vector in, and we know that the vector in is perpendicular to the vector P naught, we know, what do we know? So this vector is perpendicular to the plane, and we're going to have a vector perpendicular to our vector P naught. And so what do we know about that? Do you remember that if you dot two things that are perpendicular to one another, if you do the dot product on them, you get, do you remember? It's 0, right? So if we were to dot in with P naught P, that vector, we ought to get 0 because they're perpendicular to one another. So then we're going to be dotting A, B, C, that's our normal vector, with this vector here, x minus x naught. That's my dot for dot product here, y minus y naught, and z minus z naught. And so when I'm going to say that's equal to 0. And so when I put these together, this is going to be a times, remember you multiply them and add them, b, y minus y naught. So I'm multiplying them and adding them. And c, z minus z naught, right, equals 0. If I multiply this out, I get ax plus minus, really, just kidding, just checking you, minus a times x naught plus by minus by naught plus cz minus cz naught equals 0. And this could be the equation of a plane, but this is not typically where they leave it. They typically manipulate it a little bit, and so we're going to do that as well. They put the x's, the y's, and the z's all on one side, so I get ax plus by plus cz equals, and then they put on the other side of the equation the ax naught, the by naught, and the cz naught. And so this would be ax naught plus by naught plus cz naught. And this is a lot of times called d, is what it's a lot of times called. And then that's the equation of a plane. If you're kind of remembering what we gave as the equation of a plane, it's just different by capital letters. And back in, I think it was 12.1 or 12.2, they said that the equation of a plane was ax, right? Do you guys remember? By plus c, z equals d. And yeah, just, right, just capital letters versus lowercase letters. And so, yeah, so hot diggity dog. And I've just summarized that down here, that a scalar equation of a scalar equation of the plane through the point, this, with the normal vector, this, is given here, or given here, where d equals ax naught plus by naught plus cz naught. Remember, this is the normal vector. So we're going to give a try to this and see how we do. And we're going to be like, hot diggity dog, is what we're going to be saying. And so I'm getting these papers here. I think this is our next one. This is our first example here find the equation of a plane. Oh, I should set those over there, but they will fall. And so this table is not as long as the table as I had before, but it is what is available, and so you use what you got, right? Okay, find the equation of the plane with this point that is parallel to this plane right here. And so if it's parallel to this plane, so it's parallel, right? The two planes are parallel. What is that? What do you need to find the equation of a plane? I guess, first of all, we'll start there. Yeah, you need a point on the plane, or in the plane, whatever you want to say. And you need a normal vector. A vector that's normal to the plane. And so here's my planes, right? Here they are. My two planes are my hands here, and they're parallel to one another. And so what does that tell you about their normal vectors that are coming perpendicular to each of those planes? Yeah, they're parallel to one another, and that means that they are scalar multiples of one another. And so we need a point on the plane. Well, they've given it. We need a normal vector, and what they've told us is that our plane is parallel to this plane, which means they have normal vectors that are scalar multiples of one another. You can even use the same normal vector. And so the normal vector here, now remember, the normal vector was the A, B, and C. And yeah, it's different than on the line, right? It's just a coefficient of X, Y, and Z, right? That's all that it is. And I circled Z instead of circling the coefficient there. But tell me what that coefficient is. Yeah, it's -1. And so this could be our normal vector. And then so the plane that we're trying to build, the equation of the plane, is, so we've got it, right? They gave it to us. And so I can use any scalar multiple. And so that means I can use this value just right here with a scalar multiple of 1. That would be just fine. I can use any normal vector, and that means any that are perpendicular to one another. So I'm going to just plop this in. And so the formula is this: AX for a plane, BY plus CZ equals, then you multiply AX naught plus BY naught plus CZ naught. And so in this case, this is 2X plus 3Y minus Z equals, and then when I multiply these together, I'm going to be getting, so I'm multiplying, this is my X naught, Y naught, Z naught. I'm going to be getting 6 here, plus 18, plus 2. And so when the dust clears there, I get 26. So there's the equation of this plane. I'm like hot diggity dog, and it fit in there pretty nicely. And then just some strategy. If you're asked to find the plane and you're given 3 points, then you can use, and I should have put here, when I put that, should have put that these 3 points are not on the same line. And so not all on same line. And then you can use those 3 points to come up with 2 vectors, not necessarily the same 2 vectors in the plane. And these vectors, when you do, will be 2 non-parallel vectors. So they could start you off with 2 vectors in the plane and ask you to find the equation of the plane. They could ask you to start with 3 points. You could use those 3 points to come up with 2 non-parallel vectors. If they start you off with vectors, 2 vectors, they need to be not parallel with one another. Then what you want to do is you want to find the cross product of the 2 vectors that you have to get a normal vector that is normal to the plane. And I wish I would have had here to the plane And so you guys are getting to fix up my notes a little bit here, and I'll get them fixed up for the lovelies next semester. And then boom, you'll have a point. In fact, you have 3 points, but you can use any one of them, and you'll have a normal vector after you cross multiplied. And boom, you can then plug it into the equation of a plane, and you'll know the equation of a plane. So that's kind of the story. So we're going to give a try to that on here. They've asked us, they've said, find the equation of a plane containing the points, and then I have these points. And I can use any I can create any 2 vectors I want. So I'm going to create the vector PQ. But I could have been saying to you, hey, I want to do RP right now. And it doesn't matter. And so I'm going to do, and so this was P. And so I said Q, so I'm going to go 1, take away 2, -1. And then -2, take away 3, -5. And if I make a mistake on my arithmetic, I'll say a cuss word. So I'm going to try not to do that. 3, take away -1, 4. I can't be talking, like that on these videos, because my mama might watch them, and she doesn't want to hear that kind of talk, or worse than that, my priest. And so, so I'm going to keep it clean. Then I can use I can't use QP because they would be parallel with one another. And so, but I could use either PR or QR, and that's my choice on what to use. I'm going to use QR just because when I did this problem earlier, I used QR, and that will keep my arithmetic good. And so that I can verify my arithmetic, since I really don't have anybody here other than my cat, Susie, who looks like she's going to jump on my lap, to verify my arithmetic. So -1, and I was going to do Q, -1, that would be -2. So I'm creating the 2 vectors that are not parallel with one another. And then 2, take away -2, that's 4. And 4, take away 3 is 1. Okay, so I have these 2 vectors, and they're not scalar multiples of one another. So cool, I can go on to the next step, which is I want to come up with the normal vector. And this is 2 vectors in my plane. And if I cross them, I will come up with a normal vector to the plane. It'll be normal to both of these vectors, and it will be normal to my plane. And so that's kind of my idea. So I'm going to cross them and do the cross product. I'm going to call that N, my vector N that I'm trying to find. And you get a rhythm of how you do the cross product on things, and I'm cool with that. So I know that I do the cross product a way, and a certain way. I think that it's the same way your book does the cross product, so it's not unusual way of going, and I'm okay however you do it. And so because I don't want to make a mistake, I put out here my I do minus, and then my J, and then I do plus, and then my K. That's what I do. And then I come here in between, and I put the minus that's in between, because now I'm just going to multiply these. You do you. I mean, it's however you want to go. Then I put my finger over I, and I multiply those together, and I get -5. And then you're supposed to subtract this, but I've already put the minus there, and so I get 16. And then I put my finger over J, and I do the same thing. My finger's too wide, and so I have to die it for my finger. And so I'm going to get -1, and then I'm going to get -8. And I got a double negative there. And then I'm going to put my finger over K, and I'm going to get -4, and I'm going to get 10. And I've already put the negative in there because people say subtract, and the crisscross applesauce right on our cross product. So when I do this, I get -21 I, and then I get -7 J, and I get -14 K. And I do like to have those little hats on there, and I didn't put them on there, so I'm going to go put them on there. So there they are. Now I can write that in this form here, or I can also write it in this form here: -21, not negative 2, negative 7, negative 14. My choice on how I write then. And I'm also okay with you going from here right into this form as well. I'm fine with that as well. How that would look is instead of having the I, J, and K, you would just have here in my brackets negative 5 minus 16, but you wouldn't have the I, and you would be putting it in the first spot, and great, wonderful. And then you want to make sure you put your negative in there for your J, and then you don't need negative for your K. So great, if you want to do that, that would be just lovely. However, you know, it's all good. And so now I have found the normal, and so any scalar multiple is also a normal vector to the plane. So if I wanted to, I could pull out, they all have 7 in common. In fact, they have negative and 7 in common, and I could use that if I wanted. So I could use for my normal, if I liked, I could pull out a negative 7 from each of these, right? This is negative 7, and this is times 3, times 1, times 2, right? Do you guys agree? And then I could just use a scalar multiple. So I could use 3, 1, 2 if I liked. So I'm going to use that for my direction. And so my plane, remember how it goes, it's ax plus by plus c z equals ax naught plus by naught plus c z naught. And we have here 3x plus 1y plus 2z. That's a 2, and that's a z. And then now we're going to multiply them, and we can use any point we want. I'm going to just use P as my point, just because it's first, and there's nothing particularly wrong with P. If they had a lot of fractions, I might not want to use that. And so you would multiply these together, and you would get 6 plus, and then I would multiply these together, and I would get 3. And then I would multiply these together, and I get negative 2. And so when the dust clears, over there, I get 7. And so this is 3x plus y plus 2z equals 7. And there's my equation of a plane. Whoops, I lost it. And so there's my equation of a plane. So we did a lovely job on that. One's beautiful and not too bad. And now, we're tired. We're weary, but we're continuing on in our weariness. And so we're gonna do another example, and we're gonna think about our basic strategy here. So here's our, so maybe too many examples, but try to kind of give all of the different ways I saw it in the textbook, asking questions. I'm gonna try to get that off the screen. Put it over there, and I'm gonna lose it. Ask you guys where it is, and you'd be like, well, we couldn't see it. I don't know where you put that paper, but it was showing through. So they said find the plane containing the point, and they gave us this point and this line, and so we've got to kind of think about our basic strategy. So kind of the idea is that if you what you need is you need 3 points in your plane, and so I've been given 1. I could use this line to find the other 2. The other thing that I need is a way to find my plane is I need 2 non-parallel vectors in my plane, and I could use this line. It has because it's a line, right? It has a direction vector, so that would be a vector in the plane, and then I could find a point that's on this line, and I could create a vector with this other point here, and then I would have 2 vectors that are not parallel to one another. I'd have the direction vector and this other vector that goes from a point on the line to this point, right? And so that's kind of my strategy. And so is to, anyway, so that's my strategy, is to come up with either 2 points on this line, which I could do, or a vector from this line and a point from this line, and then I'll use that point with this point to come up with 2 vectors. And so that's going to be my strategy. Both of those things will work though. Either one. So the direction vector, and I'm going to call it V, and I don't know if you guys remember where the A, the B, and the C on the direction vector are, is right here, 2, -3, and 5. So that's our direction vector. And then I want to find a point on this line. So any point on this line. And I don't know if you guys remember, but the form here was x minus x naught over a, right? And so the a was the direction part, and this x naught was a point on the line. So a point on this line was 2, is a point on this line. So I'm going to call, this one's already named P by me, that point. And I'm going to come up with this point Q. So a point Q, and point Q is on the line. And I'm going to use 2, right? And then remember how this goes, y minus y naught over b. We already got the direction part, -3, right? And so right here, it needs to be a minus there. So this is -1. And then the equals z minus z naught over c, right? And so in this case, we have a plus, and we need it to be a minus, so it's -3. So now I have a direction vector, not the normal vector, but I need a normal vector. But how it goes is that I use 3 points to come up with 2 non-parallel vectors. Well, I already have 1 non-parallel vectors. I'm going to use these 2 points to come up with a second vector, direction vector, and then I will cross those together, and that will give me my normal for my plane that I need. And so I'm going to do either PQ or QP, it doesn't matter. And in that case, this is going to be 2 minus 3 is -1, and -1 minus -4 is +4, so -1 plus 4, that's 3. And -1, yeah, 3 is right. I'm sorry, I was checking my math. -3 minus 5 is -8. So now I have a point, and I have 2 vectors, but that are in the plane. And these 2 vectors are not scalar multiples of one another, and so I can cross them and come up with a normal vector to my plane. And so that's what I'm going to do next. So my normal vector I, J, K, and it doesn't matter if you do V cross P, Q, or if you do Q cross VP, it doesn't matter. V cross PQ or PQ cross V, it doesn't matter. So I'm just going to put V on top here. And so is that what I did when I did it before? Did I put V on top? That way I'll be able to check my math. I actually put PQ on top, but it does not matter. And so I'm going to just follow what I did before so that I can have a way of not making an arithmetic mistake. And I'm going to try this time writing this in vector form, just as the practice of doing it. This is how I do it when I write it in vector form. Notice my negative on my J. And there are other ways of doing it, and I'm okay with you doing it other ways. Here's a negative in here. And I've heard people say that you can, this, I don't have enough room in here, and that's going to make me go crazy and then be calling people names. And so, which is not a polite way of acting. So there's my pieces, and I have my minuses in here, and I'm going to go fill them in. So for I, this is 15, and then it is 24. So subtract negative, right? Subtract, and then I multiplied, so 3 negative, so I get a minus. And then my chubby finger, I get -5, and back the other way, -16. And then I'm getting +3, and then back the other way 6, and I already put my subtraction in there. And so when I do this arithmetic, I'm getting -9. And then in here, I'm getting -5 plus 16, which is 11, so -11. And then here, I'm getting 3 take away -6, so I'm getting -3. And this is my normal vector. And remember, I can use any scalar multiple. So if this had been a 12, I'd be dividing out a 3, but I still might want to divide out a -1. And so if I divide out a -1, this would be 9, 11, 3. And then I can use that as my normal vector. And so remember how it goes together for my plane, right? I've written the formula so many times that I hope that you have the formula, because it's not very tricky. And so I hope that you have it memorized. And so, because it's not very tricky, but I wrote it wrong. I wrote Z because I was talking and thinking about ice cream. I know for sure I was thinking about ice cream because that's usually what I'm thinking about. And so my A, my B, and my C are 3, 11, and 9, 11, and 3. So this is 9x plus 11y plus 3z. And then I'm going to multiply this vector A, B, C, my normal vector, by the point, and I'm going to use this original point that they gave me, even though I found another point that I could use as well, right? And so I'm going to multiply these together, and that's going to be 27, -44, and 15. And so, long story short, when I do the arithmetic there, 27, got to get a calculator, right? So hopefully you're doing this along with me and not just watching me, because that's not very helpful. Hopefully you're thinking about what you need and how you could put it together, and I'm hoping that you're saying that, boy, you do it so slow, and that I can go much faster than you and put it on there. So we did a lovely job on that. Okay. So here's another one that we're going to try, and it's asking us to find the equation, find a plane containing these 2 points that is orthogonal to the plane, and then they've given us this plane. And so they're saying that it's orthogonal to this plane. And so what we need in order to come up with a plane is we need a point, right? And we need a normal is what we need. So for a plane, we need a vector, a normal vector, and a point on that plane. And we've already been given the point on that plane. And we also need the vector that's normal. And we know, I'm going to call this, the plane 1 is the plane that we're trying to come up with. And I'm going to call this plane 2. And what they're saying about that plane 2 is that they're saying that it is orthogonal to our plane. And so pretend with me that this piece of paper is the plane that we're trying to come up with, plane 1. Then they're saying that there's a plane that comes and is meeting this plane orthogonal. So you can see this plane, right? And then it's meeting orthogonal to that plane right there. And what we need is we need the normal vector for the plane that we're trying to find. We know the normal vector for this plane. And what do you guys know about them? So you can kind of see what we kind of got going on. So this is the plane I'm trying to find. Pretend with me. And we know that there is a plane that's orthogonal. And I can find the normal vector to that orthogonal plane. It's, in fact, the normal vector for plane 2, as I called it, is equal to, can you tell me what it is? It's 2, 3, negative 4. And that vector right there, and I want to vector right here, right? This is what I'm wanting to find, and I just found this vector right here. And what I'm knowing about this vector right here with the vectors of this plane is they're perpendicular with one another. Do you guys agree that they would be perpendicular with one another? So this vector right here, do you guys agree? I'm going to put it here. Here it is. That vector right there, it's normal. And do you guys agree that it is a scalar multiple of a plane, of a line, of a vector that's in the plane that we want to find the equation of? And so we can use, we can find a vector, another vector in our plane, and a vector in our plane that is, this right here is a scalar multiple, would be parallel to a vector in our plane, that we're trying to find. I called it plane 1, right? That's the plane we're trying to find. Then I'm going to call this P, and I'm going to call that Q. Then PQ is a vector, so let's find it here. 1 take away 2, negative 1. 3 take away 1, 2. Negative 2 take away 1, negative 3. This is a vector in our plane. In plane 1. And so, since I have, this is 2 vectors, this one's a scalar multiple of a vector in our plane, but since I have 2 vectors essentially in our plane, if I cross them, do you guys agree that I would get a normal to the plane that I'm trying to find, plane 1. And then I have a point in plane 1. I have 2 points in plane 1, in fact, and I can put it in the formula. So this is going to be the normal to plane 1, the one that we're trying to find. So I, J, K, and then it doesn't matter what you put for first, because we're going to be crossing these two. And so I'm just going to follow what I did before, which is I put the 2, 3, negative 4 here, just so that I can check my arithmetic. If I put them out of order, then I really could check my arithmetic as well, because they would just be negatives of one another, right? And I'm going to write this in notation with the angle brackets. And so in my cute little way that I do, you do you though, and don't be discouraged by doing it a little bit differently. With I, J's, and K's would be okay. And then my finger over I, so that's negative 9. I already have the subtraction in here, so that's negative 8. Finger over J, and so that is negative 6. And when I multiply negative 1 times 4 is positive 4. I already have the subtraction in there. And yeah, I had to put remember it's negative of J in the formula. And then we get putting our finger over k, we get 4, and then minus 3. So when the dust clears, we're getting -1 here. This is our normal to plane P1, plane 1. Is that okay? And then here I'm getting -10, +10, and here I'm getting 7. And I don't see anything nice that I can pull out of that like I did on the others. And so I'm gonna just leave it like that. And so remember the formula: ax plus by plus c, for this is the plane builder, cz, equals ax naught plus by naught plus cz naught. You do get where you don't have to write it out. I'm writing it out for you, and trying to be helpful to you on putting it together. And so let's see here. This is our A, our B, and our C, and this is going to be our x naught, y naught, z naught. And so this is -1x, or negative x, plus 10y, plus 7z, equals, and then multiplying these together, -2, +10, +7, and 17 take away 2 is 15, I think. And we did an excellent job on that one. And so it was not too bad at all. And so anyway, so that's kind of our story on that, and we're going to go and look at what we got more to go on here and see how that goes. I just want to show you that if you had used the other point Q, if we had used the other point Q, then we would have been getting -1, right, for this other side of the equation, right, because ax naught, right? So if we had used this as our x naught, then we would have been getting -1, and then we would have gotten 10 times 3 is 30, plus 30, and then minus 14. And I don't know if you noticed, but that is also 15. So we get the same value. So we could have used the other. Okay, so we did a lovely job on that. I'm throwing that over here and getting another one here. And oh my, oh my, oh my. And that is not the right paper. Sorry. Page numbers, you guys have told me to put on there, and I'm typing chapter 13 notes, and I've got page numbers on them. Okay, planes are perpendicular if their normal vectors are perpendicular. That means their dot product is 0. Planes are parallel if their normal vectors are parallel, scalar multiples of one another. The angle between the planes is the same as the angle between the normal vectors, which it's good that we can do things with the normal vectors, because that's what we're trying to, that's what we can find easily on a plane, is the normal vector. And then we recall that to find the angle between the vectors, it's cosine of theta equals, and then you dot the two vectors with one another and divide by their magnitudes. And so anyway, so they're asking us to determine whether the planes here are parallel, perpendicular, or neither. If neither, find the angle between them and round to the 10th. So that's what they're asking us to do. So the first thing I want to make sure of is they're not parallel. And the easiest thing on parallel is to check if they're scalar multiples. So I'm going to get the normal vector, I'm going to call it N1 for plane 1. And remember, it's just the coefficient. This is our 3, our -1, and our 2. So there's that normal vector. And this is the normal vector for plane 2. It's 2, 3, and 1. And if they were parallel of one another, they would be scalar multiples. But you can see that those are not scalar multiples. So since they're not scalar multiples, they're not parallel. Then I want to know if they are perpendicular. And to test whether or not they're perpendicular, so that's what I ask myself next, is are they perpendicular, right? And so when I ask myself, maybe I shouldn't be writing that. Could get me banned off of YouTube. Perpendicular. I was looking how to spell perpendicular. I'm so tired. That would mean that their dot product is 0. So I can definitely dot these together, and let's see if their dot product is 0, right? That's the test. So if I dot them together, you multiply and add. So this is going to give us 6 plus -3 plus 2, which doesn't equal 0. So that tells us they're not perpendicular. If this had equaled 0, we would have been able to say that they were perpendicular, and then we would have been able to be done, right? So that would have been great. And so now they're asking us to find the angle between them and round to the 10th. And so they said that all we have to do to find the angle between them is to find the angle between the normal vectors, and the angle between the normal vectors. In this case, instead of having u and v, we're going to have n1 and n2. So this is going to be that the cosine of theta. So now I'm trying to find so this means neither. I'm going to write down here, neither. So these planes are not neither, right? These planes are not parallel with one another, right? Stacked on top of one another, the planes. They don't meet at a perpendicular angle. And so there's some other way. And that means they cross somewhere, and we're going to find at what angle do they cross. So they're neither parallel or perpendicular, and now we're going to find the angle that they cross at. So this is n1 dot with n2 divided by the magnitude of n1 times the magnitude of n2. And the good news is well, we already up here we had already done the dot product, and when we did the dot product, we didn't get 0. We got is that 5? We got 5, and so this is the numerator here is equal to 5, and then we want to go through and find our magnitude. And how you find your magnitude is you square each piece, and add them together and then square root it. So this is 9 when I square it, and I add it 1 squared, right, and 4. It should always be positive when you square it. So if you square a negative, you get a positive. So I just don't even worry about the sign. And 4, 9, and 1. And so what I'm getting here, coincidentally enough, is 14 in the denominator. Square root of 14 times the square root of 14 is 14. So 5 over 14. Usually when they ask you to find the angle, they're asking you to find the acute angle, and I'm going to find that acute angle here. And so this is going to be the theta equals the arc cosine of 5 over 14, right? And that's the exact value right there. So if they'd asked me for the exact, that's the exact. And then if I want to approximate that, so this is the exact value right there. They asked me on this problem to round to the 10th. And so typically you want to tell both if you can. And so my calculator is in degrees. So arc cosine of 5 divided by 14. I'm getting 69.07, so to the 10th would be 69.1 degrees. So the angle, I'm just going to put that here, this is approximated, is cosine -1, 5 over 14, which is approximately equals 69.1 degrees. So we did a lovely job on that, so I'm answering both questions. Neither on parallel or perpendicular. And then the next thing here, oh, there goes another calculator. I have a crazy situation going here on this desk. It's got a hangover is what it's got. And I set things on the hangover and they fall. And so now here we go. To find where a line and a plane intersect, all you have to do is plug the line into the plane. And so they've asked us find the point where this line, and so they've given this line in parametric equations, right, in parametric form, and they want to know where it intersects the plane, and all you have to do is plug in. So we'll get 2 times x. Well, x is 2 plus 3t plus 3y, and y is negative 1 plus t, and minus z, and z is 3 plus 2t, and that equals 9. And then I'm going to do a little algebra magic here, distributing along here, and try not to make any algebra mistakes, because that really ticks me off when I make an algebra mistake. I feel like I should be beyond algebra mistakes. I tell my Calc 1 students that what you should do is you should get someone who's learning algebra, and you should volunteer to tutor them to keep your algebra. I got a T on there. That's not right. I don't know why I put a T on there. 3 times negative 1 is negative 3. I need to get an algebra student and tutor them is what I need. So when I put these together, 6t, 3t, and minus 2t, I'm minus 2t. Oh, I wrote this down wrong. And oh my gosh, I was just talking about algebra mistakes. But this was a typo. This wasn't an algebra mistake, right? I brought down the wrong, and this is a plus. I've done this problem before. I probably wouldn't have caught that mistake, but I'd done this problem before, and I knew that I was supposed to get 11t, and I was like, I'm not getting 11t. What am I doing wrong? And I had a typo there, a typo when I brought it down. Probably because I was talking at the same time that I was solving, and I was talking about being careful on my algebra. And when I talk about being careful on my algebra, that always causes me not to be careful on my algebra. And so I get 11t equals 11. I don't know if that happens to you. And t equals 1. Anyway, I was telling the story about telling my Calculus 1 students that they should get an algebra student and tutor them. And one of my students asked me, he said, now, how much would I charge the algebra student when I tutor them? And I said, well, you don't understand. You're tutoring them to make yourself better and to get your algebra stronger. So really, you should be paying them. And I suggest $20 an hour and a pizza. And so you just get somebody and you say, I'm going to show you some algebra, and I'll pay you to watch this algebra and to participate, I guess, in it, ask questions, $20 an hour and a pizza. Okay, that's what I need to do. Now, I wanted to find the point where they intersected, and I know that they intersect when t is 1. And so all I have to do is put in that t is 1 back in here, and that'll find the point. So x equals 2 plus 3 times 1, right? And so that's given us 5, and y equals negative 1 plus 1 is 0, and z equals 3 take away 2 times 1, which is 1. So the point is 501, where the plane and the line intersect one another. So we have a plane is like a piece of paper, right? And a line is like my pencil, and they're intersecting one another, and this is the point that they intersected one another at. Okay, we have in our notes only one more page to do, and I have a typo on there to fix, and so we'll fix that typo. And there's 2 ways of doing the problem, and so you can do it. So right here, both 2, it needs to be gone. So right here, 2, both 2, it should have been just 2. And I'm going to show you the way I thought of to do, and here in the video, and then I described to you the way that I saw someone do on the internet, and and I thought that their way was really super clever, but my way's not bad either, and and so anyway, so I'll describe to you, I guess, because I've got that up there telling you the way the person on the internet did it. This is the way I thought to do it. Find the equation of a line of intersection of the planes and find the angle between the planes. Okay, so I want to find a line. What does it take to find a line? What do you have to find the equation of a line? Well, you have to have a point, and a point, and you have to have a direction vector is what you need, the direction vector. So those are the two things that you need. Alternatively, you could have 2 points on your line, right? And if you have 2 points on your line, then you could use those 2 points to find a direction vector, and then you would have a point and a direction vector, and then you could find the equation of the line. Okay, so that's what I thought of. So I said to myself, I need 2 points where these, because when these two planes intersect one another, which they're telling you they're going to intersect. So here's plane 1 and here's plane 2, and I've got them intersecting one another, and you can see that they intersect each other at a line. And so, and I think that it even told you that. Find the equation of the line of intersection of the two planes, right? So it even told you that was going to be a line. And so what I need to do is I need to come up with any 2 points on this line. And there are infinitely many points on this line. And I just need to come up with 2 of them. And so to find any 2 points on the line, what I wanted to do, and they have to be on both planes as well. And so I just arbitrarily chose x to be 0. X is 0, right? So here and here, x is 0 in there. This should have a little space there. It almost looks like it's 2x, but it's not. And so, but it's just x. But I'm going to choose x to be 0. So from plane 1, when I choose x to be 0, I get negative 3y plus 4z equals 3. And from plane 2, I get 4y minus 2z equals 7. And I'm going to solve that to come up with x and y, and that is going to be a point on the line where the 2 planes intersect. This will be a point in both planes and on the line of intersection. And so when I want to use 2 equations, 2 unknowns, so I'm going to multiply here by 4, and I'm going to multiply here by 3. You could do it differently, it doesn't matter. And so I'm going to get here negative 12y plus 16z equals 12, and I'm going to be eliminating y because I got 12y, and then I've got minus 6z, and then I got equals 21. So when I add these together, I'm going to get 10z equals 33. And so that z equals 33 over 10. So there are infinitely many points in the plane 1 where x is 0. And there are infinitely many points in the plane 2 where x is 0. And if I want to find a place where x is 0 on the line where they intersect, well, z will be 33 over 10. Now I'm going to use that z is 33 over 10 to find y. So I'm going to use plane 1. It doesn't matter. So plane 1 gives negative 3y plus 4 times 33 over 10 equals 3. So negative 3y equals, and then I'm going to put in my calculator, 3 take away that. So I have a different calculator now. So I want to do 3 take away 4 times the fraction, 33 over 10. And I'm getting here negative 51 over 3, 5 over 5. And I'm going to divide that by negative 3. So divided by negative 3. So this tells me that y equals 17 over 5. So now I have a point on the line. And that point is 0, 17 over 5, 33 over 10. Okay. Trying to find the equation of the line. And so my thought is, well, why don't I find another point on the line? And I could let y equal 0, or I could let z equal 0, and find another point on the line. And so either one will work. It doesn't matter. So let either x be 0 or y be 0. I'm going to let, no, I already let x be 0, z be 0. I'm going to let z be 0 because I happen to know that turns out not too bad. And we might as well use a break. So when z is 0, we get from plane 1 2x minus 3y equals 3. And from plane 2, x plus 4y, because remember z is 0, equals 7. And I'm going to multiply here by negative 2. And I'm solving this system of equation. So when I multiply by negative 2, I get negative 2x minus 8y equals negative 14. And if you add these together, you get negative 11y equals negative 11, so that y equals 1. And if you plug that in, 2x minus into plane 1, 3 times y, which is 1, equals 3. 2x minus 3 equals 3. 2x equals 0. No, 6. Sorry, just checking you. 6. If I add 3 to both sides, 6. Right? And so then I get x is 3. So this is a nice point. Another point. And that point is 3, 1, 0. Okay, now I have 2 points. And what I need in order to find the equation of that line, oh, and the angle, I got to find the angle too. You can see I don't have enough room here. And I'm really, 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 really sorry. Now I have written really, really big, but I still am really, really sorry. And so the other method, if you do the other method, which is described up here, and you can see me and talk to me about it if you want, if you try it. It doesn't actually take as much room, but that's not what I thought of. So I just wanted to show you that, you know, there's different ways of doing things, and this describes a way of doing it. You're going to get an answer that's equivalent. So the next thing I need to know is the direction vector, right, for the equation of the line. And you can use any 2 points on the line, P and Q, and find the direction vector. So you just need 2 points on the line, and you can find the direction vector. So I have here, the way I've written it, it's Q, which is 3 minus 0, 1 minus 17 over 5. I'm getting a calculator. 1 minus 17 over 5, negative 12 over 5, and 0 take away 33 over 10. So this is our direction vector, and I don't typically like my direction vector to have fractions in it, but you can use any scalar multiple. So I can multiply here by 10 and get a direction vector that's just as good, and so I'll use it. So when I multiply by 10, I'm going to get 30 times 10 here would make negative 24, and times 10 here would make negative 33. And then all of a sudden I can't stand it. I notice, well, they all divide by 3, so I could divide by 3 if I wanted. If you're saying, or could I just live with that? Well, yeah, you could live with that too. So this is going to give me for my direction, the real direction vector that I'm going to use, 10, negative 8, negative 11. is the direction vector I plan to use. And so, and then putting that in the form, did they say what the form of the line that they wanted? Find the equation of the line of intersect. They didn't. So I'm going to write on the other side. So on the, I had to have more room, and I'm really sorry. So I have a direction for my line vector of 10, negative 11, no, negative 8, and then negative 11. And I have a point. So this is for my line, right? And I had a point. I could use this point, or I can use this point. This one has fractions in it, so I'm going to use this one, 3, 1, 0. And so this is my A, my B, and my C. This is my X naught, my Y naught, and my Z naught. And the equation of a line, they didn't say what form, so I'm going to put it in the symmetric form, which is Y minus Y naught over A, like that. And the same for the, excuse me, I said Y's, but that was for the X's. And the same for the Y's and the same for the Z's. So this is going to be X minus 3 over 10 equals, and then Y minus Y naught over B, right? And so Y minus 1 over negative 8 equals, and then Z minus Z naught, right, for my formula, over C, minus 0, so I don't have to write that, over negative 11. So here's the equation of the line, where the two intersect one another. Okay. Now, if you want to find the angle that they intersect at, well, you have the normal vectors for the plane. I don't know, did we state those normal vectors for the plane? I didn't. But remember that if you want to find the angle of intersection, that you can find the angle of the normal vectors, and then that would give it. So for the angle, then I have the normal vector 2, negative 3, 4. So I have normal number 1 is 2, negative 3, 4. And then normal number 2 is 1, 4, negative 2. And yeah, I need to fix this spacing issue that I have there, because it's not 2x, there should be a little bit of space so that you could see that the coefficient there is 1. Okay, so, and then I have choices of what I would use, right? I could use this to find the angle. Cosine of theta equals dot in this case they're in 1 and in 2, and divide by the magnitudes. Or you could use this formula that I don't know if you guys remember, but I'm going to write it with A's and B's because that's what we have written it from, and then you can change it into N's and in 1 and in 2. And so if you do the cross product and then do the magnitude of A and B, and then this is equal to A, do you guys remember this? B, and then sine of theta. So you can solve this you can divide by these two things, right? And instead of A, we have N1, instead of B, we have N2, and then you can do the arc sine. And they give you the same answer, so it doesn't matter. And so it's your choice on whether or not you would, I'll write this so that you can see that, yeah, I was writing my memory verse of my formula for not B, N2. I'm really tired and really hungry, and it's all I can think about is what I might eat, and if I would have a little nap on my bed. So anyway, so your choice on which one of those that you would use to solve for theta. I would rather do the dot product than the cross product. But if you had done the other method that I described, then you had already found the cross product. And if you'd found the cross product, then, well, then you could do that. So this would be a good one to use. So cosine of theta, this used exactly double the room that I gave you. 2 minus 12, it's really nice when you line them up, minus 8, and then over 1, no, I'm going to do the first one first, the top one first. So 2 squared is 4. Squaring that is 9. Remember, no signs. Plus 16. And 1 and 16 and 4. So this cosine of theta equals, so I'm putting this in my calculator, 2 minus 12 minus 8 is negative 18. And square root of 4 plus 9 plus 16 is 29. And 1 plus 16 plus 4 is 21. Okay. And we're looking at where two lines the two normal vectors intersect one another. And I'd like to tell people the acute angle. They didn't tell me to tell them the acute angle, but that's typically what they're looking for when you're looking at two vectors intersecting, is the acute angle. So the acute angle, your book tells you hang absolute value around that to get the acute angle. And so anyway, so if I do that, I'm going to get theta equals the arc cosine of 18 over the square root of 29 times the square root of 21. And I don't know where my arc went to, but it's there somewhere. I might put that in my calculator if I'm giving the exact value. I think it asked me to round, but I might put that in my calculator just to, so I'm putting that in my calculator just to show you that, hey, you know, it will make it nicer if it's possible to be nicer than that. And if it's not, I'm good with that too. It apparently it wasn't. And so we'll call this the exact. I don't want a decimal in there. And then I'm going to erase this because I was hoping it would simplify it up, and it said, no, that one's too bad. That one's terrible. And so I'm going to do the arc cosine of that answer because I already put it in there. And I'm getting 43.2. That's not the answer that I got when I did it before. Make sure your normal vectors are right. 2, negative 3, 4. 1, 4, negative 2. They are. And make sure you crossed them right. 2, negative 12, negative 8, and that is negative 18. 4, 9, 16. 4 plus 9 plus 16 is 29. And 1, 16, 4. 1 plus 16 plus 4 is 21. And the arc cosine of 18, calculator is in degrees, 18 over the square root of 29. I'm going to put a times in between because I'm worried that maybe I messed it up when I put it in my calculator. 21 I'm still getting 43.2. Okay, I'm going to go with that, and I'm going to see if I have made a mistake when I did it before. And if I haven't, then I'll be happy. Okay, I think that's the story on that whole, oh my goodness, that was a lot. Okay, bye.